Have you ever stopped to think about how you can stream a movie from a server halfway across the world while you're sitting on a train with almost no buffering? It's not magic, it's routing, the absolute unsung hero of the internet. So today, we're going to pull back the curtain on the incredible split-second decisions that make our entire connected world work.
Seriously, it feels like it should be impossible, right? You click one button, and a little packet of data starts this epic journey through a global maze of cables and routers. The fact that it gets where it's going in the blink of an eye, well, that's all thanks to the incredible smarts of routing protocols, which are constantly making these high-stakes decisions for your data. I think the best way to picture routing is to think of it like a super intelligent GPS for your data. But this isn't just any GPS. Imagine one that knows about every single traffic jam, every road closure, and every brand new shortcut, all updated in real time, all across the entire planet. That's what we're talking about here. See, the internet is basically a living, breathing thing. It's always changing. The routers are the brains of the operation. And these routing protocols, that's the language they speak. They're constantly gossiping with each other about the state of the network, making sure your data can get around any obstacle that suddenly pops up. So, okay, how do these routers actually build their maps of the internet? Well, it turns out there are two competing philosophies, almost like two rival schools of thought that have shaped everything. It's really a battle between two completely different ways of thinking about knowledge and trust. On one side, you've got what I like to call routing by rumor. That's the distance vector approach. Think about trying to navigate a new city just by asking the person on the next street corner for directions. It's pretty simple, sure, but you're always working with secondhand info. On the other side, you have link state protocols. This is like giving every single router a live satellite view of the entire network map. It's a ton more information to handle, but the result is that everyone has a perfect, totally accurate map to work from. All right, let's dive into that routing by rumor idea first. This is the world of distance vector, and its most classic, old-school example is a protocol called RIP. So RIP is kind of like the original town crier of the internet. Every 30 seconds, like clockwork, it just shouts out its entire list of directions to its immediate neighbors. Its decision-making process is super simple. It just counts the number of routers, or hops, to get somewhere. The path with the fewest hops, that's the winner. But here's the catch. It has no idea if one path is a brand new fiber optic line and another is an old, slow connection. To RIP, a hop is a hop. And that simplicity, well, it comes at a huge cost. And this number right here? This is RIP's fatal flaw. 15. In the world of RIP, if something is more than 15 hops away, it might as well be on Mars. The router just considers it completely unreachable. Now, back in the 80s, for a small office network, that was totally fine. But for the global internet we have today, yeah, that's a complete non-starter. But the real killer for RIP is how slow it is to converge. That's just the fancy word for how long it takes all the routers to agree on a new map after something changes. So if a connection goes down, a RIP router might just keep sending your data down that dead-end path for minutes, like a driver following an old GPS right into a giant construction pit. All that data, it just gets lost, and that leads to some really frustrating outages. So all those limitations with RIP forced engineers to come up with a totally different way of doing things. Instead of just relying on rumors from their neighbors, they asked, what if every router had a complete, totally up-to-the-minute map of the whole network? This is that satellite view idea, and it's the philosophy behind link state protocols like OSPF and ISIS. Link state protocols like OSPF and ISIS are way, way smarter. They don't just count hops, no. They use a metric called cost, which is usually based on bandwidth. A super fast fiber link gets a low cost, and a slow, flaky connection gets a really high cost. Every router builds an identical map, and then it runs this brilliant algorithm, Dijkstra's shortest path first, to figure out its own personal, perfect roadmap to everywhere else. So they're not just finding a path, they're finding the absolute best path. And then, you've got this really clever hybrid called EIGRP. Cisco developed it, and it really tries to give you the best of both worlds. It acts kind of like a distance vector protocol because it only talks to its neighbors, which keeps things efficient. But it's also incredibly smart, using an advanced algorithm called dual to find not only the best path, but also a pre-calculated loop-free backup path. So if the main route fails, bang, it can switch to the backup almost instantly without needing to recalculate the whole map. It's like having a pre-planned detour for every single road on your trip. Okay, so we've got the old school town crier, we've got the modern satellite mappers, and we've got the clever high-speed hybrid. Let's put them all head-to-head and see where each one really shines.
Let's break it all down. RIP is your simple, no-frills option, perfect for small, self-contained networks. OSPF is the reliable, industry-standard workhorse you'll find in most big corporate networks. EIGRP is the high-performance speed demon, especially if you're in a Cisco-heavy environment. And then there's ISIS. It's the unsung hero, the incredibly scalable beast that powers the very core of the internet, connecting all the huge service providers together. You know, this chart really says it all. When it comes to reacting to a change in the network, the difference is just night and day. Over on the left, you've got RIP, taking what feels like an absolute eternity to find a new path when something breaks. And on the right, OSPF, EIGRP, and ISIS are practically instantaneous. They can recover in the blink of an eye. And in our always-on world, that sub-second recovery time is everything. So here's the most important thing to remember. There is no single best protocol. It's just not that simple. The choice is a classic engineering trade-off. It's all about picking the right tool for the job, balancing things like simplicity against the absolute need for speed, scale, and intelligence that your specific network requires. So, where does all this go from here? We've already gone from simple gossip to routers that are practically all-knowing map makers. But as our networks get even more complex, even more self-aware, will we even need these protocols anymore? I mean, could we see a future where networks powered by AI can just intuitively route traffic without ever having to talk to each other, creating a truly intelligent, self-healing digital world? The next chapter in this story, well, it's still being written.